So in this video, I'm gonna derive you the backpropagation algorithms for the softmax classifications for the neural network with one hidden layers. And what we need is we need to derive the, okay, maybe I'll write down here. We have the input layer, right? We have the input layer, and we transformed by some first weight matrix V to the hidden layers, and then we transform by the weight W, we get output layers, and then we apply the softmax activation function after we transform from W. So in other words, we need to derive the there are two derivatives we need to solve. One is with respect to V and one is with respect to W. Actually, we apply this for the V. Okay, we first transform, multiply the input vector X, and multiply by this V, and apply to this S1 function. Okay, so this is S1 function V times X. This step you can think we applied the sigmoid or the ReLU activation function, and then we apply this. We get what the output is called H, right? The output is hidden layer H vector, and then we multiply H with W. So W times H, and then we apply this softmax function, softmax. We get Z vectors, right? And we had a Z vector, and each component Z vector is equals to E to the power W. So remember here, each W times H, W is a M multiplied K plus 1 matrix, and H is a K plus 1 vector, and for the ith row of this W matrix, multiply this H, we get the Zi. So this Wi is the ith row of W. Okay, you dot product with H. Okay, and then you divide by all the summations E to the power for each of the class. So J from 1 to M. Okay, once you get Z, you get the output is a Z, right? This is a Z vector, and then you calculate the loss, right? You calculate the loss. So the loss will equals to negative. So you get the loss between this Z vector and the label Y will equals to negative Zi cross entropy Yi. Okay, so this is our L, and then we need to derive the by doing the forward path, we can calculate all these values, but we also need to calculate the derivative of the L with respect to W and respect to V. Okay, so this requires a little bit mathematics, a little bit derivatives, calculus, not much math. Okay, here to simplify our work, let's just call this S row times H vector. We call it Ti equals to the S row dot product with H vector Okay, so therefore, this implies the derivative, the gradient of the ti is a value, right? Ti is a scalar with respect to the wi vector. This is just, you can think this is just a variable times a constant, so the derivative just is constant. So it's h vector. And also similarly, the gradient of the ti with respect to h is just equals to wi. Okay, so that's the first tool we need to use. We'll come back to this one. And also we can rewrite the loss function. So entropy, cross entropy loss zy equals to negative yi natural log zi, right? These are cross entropy, right? Cross entropy here. So I from 1 to m, we have how many labels we calculate the cross, and this can be written as summation of the negative I from 1 to m, okay, yi. Let's see what's the natural log of the, actually with this notation we can think this zi, this softmax function is just equals to e to the power ti, right? Divided by summation I from 1 to j m e to the power tj. Let's call this j. Okay, so if we take the log, here this is just equals to natural log cancel this e, so we have the ti. We have the denominator is become negative, so natural log summation e to the power tj, j from 1 to m. Okay, we have this identity. So the natural log z we can plug in here. We get ti minus natural log summation j from 1 to m e to the power tj. Okay, and then this equals to so we can just distribute this one. So summation yi ti I from 1 to, so for each label this cross classified entropy equals to comes summation I from 1 to m yi. Oh, right. And so each term multiply the natural log summation e to the power tj, right? J from 1 to m. Recall each term there is nothing about the I, no I here. So you can think this is a constant term. So this will equals to negative I from 1 to m yi ti plus and we have the assumption the yi summation equals to 1, right? And we can take the constant out and find the summation. So then this term is just simplified to j from 1 to m e to the power tj. J equals to 1. Okay, so now we need to find the we are looking for the partial derivative. We are looking for the partial derivative of the L loss function with respect to the W matrix, and we also need to find the L with the V, right? And we need to find it for each row, derivative for each row. Okay, so in other words, we also need to calculate the gradient of the L with respect to Wi, the ith row of the W matrix, which equals to. So, and then you find the partial derivative of this with respect to W. Yi is constant. There's nothing about W, but each Ti, recall the Ti has Wi, right? Ti with respect to Wi equals to H. So the first part became to Yi times H. Yi is a scalar, right? And H, Yi is a scalar times H. And for the terms, the not the ith term is disappeared, right? There's no Wi, so its derivative is 0. So we do not have summation here anymore. And plus the derivative of the natural log. Recall so derivative of the natural log is 1 over this summation term, right? So summation e to the power tj, j from 1 to m, okay? And the derivative of the inside function respect to Wi, because each term inside there is no for the term j does not equal to I, it's 0. If for the ith term, we only have the ith term now. And then we need to find the partial derivative of the t, of the gradient of the ti respect to Wi. Ti to Wi is h. Okay, here we have this result here. So therefore, this term is reduced to h. So to summarize, this equals to recall what's this? This equals to zi, right? This is definition of zi. So and both term has h. So this becomes zi minus yi times h vector. Okay. So now we calculate the derivative of L with respect to Wi. We get and we do this for each row. We get the whole matrix here. So we get this term. You can think this is just equals to z minus y times h transpose. Okay, so this implies the gradient of the L with the matrix equals to z minus y times h transpose. Okay, this is a vector, and this is a m times 1 vector, right? And this h is a h is a k plus 1. So and the transpose, this is 1 times k plus 1 vector. So this whole thing together is m multiply k plus 1 matrix. So this gradient is a gradient matrix. Okay. Okay, so and similarly we can derive the gradient of the L with respect to h, which is given by think about this term. Which term has h? Which term has h? Yi, there's no h. Ti is a Wi times h. So Ti has h. So it becomes negative. Okay, negative summation j from 1 to m, and each term the yi, right? Ti with respect to vi is with respect to h is wi. Sorry, wi. Oh, this is I. Let's use I notation. And the plus, the second part derivative, again, we have the chain rule, right? We find the partial derivative with respect to natural log is summation j from 1 to m e to the power tj. And the denominator equals to, and actually every term has h, right? Every term has h. So the partial derivative will become to summation j from 1 to m e to the power tj, and multiply tj with respect to v. To h is wi. So this is the wi. Okay, e to the power tj is a vector, each e to the tj is a scalar, wi is a vector. So this is the case, and this equals to, okay, each term has a wi, so we can take the wi out. So it's negative I from 1 to m. Okay, and the wi, take it out. And the inside is just the scalar, it's yi minus, if we take the wi out, each term inside, actually this is just summation of the zi's, right? Summation of zi. Okay, so therefore L with respect to h is equals to w transpose z minus y. Okay, so this is a gradient of this part. So now we have everything to solve the back propagation now. For example, we have the, so we have the gradient L with respect to W is here, gradient of the L with respect to H. So gradient of the L with respect to H is equals to W transform Z minus Y. Okay, and then once we calculate the gradient this one, we can further calculate the L with respect to V2. So maybe we can calculate the L with respect to the matrix V's L row, which is given by the L. We first find the partial derivative is HI, because VI is only in terms, only HI has a term VI. All the other rows does not involve the HI. Okay, so and then multiply the gradient of the HI respect to the VI. And this can be written as, maybe I need more space here. This can be written as, this equals to, the gradient of the L respect to the, maybe just use this one, gradient of L respect to HI, right, partial derivative, and multiply by gradient of the HI times VI. HI is just a scalar transformation, right? So it's an activation function. So S derivative of the VI times X. Okay. and then you take times the derivative inside this equal respect to vi, so this has x term. So this is a scalar times x. Yes, so that's all the gradient we have. So and now the back propagation means we can calculate the partial. We can calculate this zi, right? We can go forward for each w initial value w and the initial value w v. For each initial w v, we get this h. From h times w, we get this z, and the softmax function we get z. That's the forward path. And the backward path is we can calculate the subgradient of the L respect to h. L respect to h, we substitute to here. We get the gradient of the L respect to v. Okay, and by passing back to z to here, we can also calculate, and the h to here, we can calculate the subgradient of the L with respect to w, so that we can apply the back propagation. So that's the back propagation algorithms for the softmax function. But this algorithm already encoded part of the PyTorch algorithm. So in the lab, you can have more practice, Python implementation on this. And in next lecture, I'm gonna give you the last topic in the neural network called convolutional neural network. Okay, I think that's all I want to cover today. You're gonna practice more in your homework and lab.